A beam of light leaving Earth takes years just to reach the nearest star. At that pace, crossing our galaxy would take longer than all of recorded human history. Combined, the universe looks open to us, yet distance keeps it out of reach. The same laws of physics that explain reality also seem to enforce that limit. But what if that limit isn't as final? As we once thought, scientists are now exploring a method that could send spacecraft 10 times faster than light, not by outrunning physics, but by literally bending it, turning journeys that once spanned throughout centuries into voyages measured in years, with warp-like space-time effects already appearing in laboratories. If you're interested, subscribe. Hit that like button and let's discover this innovation together. To understand why the idea of traveling faster than light is so extraordinary, we first need to sit with just how severe the problem really is. Space is not just large in a poetic sense. It is vast in a way that actively resists intuition. Distances between stars are so extreme that even the fastest things we know struggle to make a dent. In them, take light itself. Light is the fastest signal in the universe, moving at about 300,000 kilometers every second. In a single blink of an eye, it can circle Earth more than 7 times. That sounds almost magical until you scale up. Even at that speed, light takes more than 4 years to reach the nearest star system beyond our own, crossing the Milky Way. A galaxy that feels compact when viewed from Earth takes light roughly 100,000 years. These not travel times, they're geological ages. Now compare that to us, the fastest. Spacecraft humans have ever built moves at a tiny fraction of light speed. Even if we sent it directly toward the nearest star and never slowed down, the journey would take tens of thousands of years. Civilizations rise and fall in far less time. Languages vanish, continents shift. A mission like that would outlast every culture that launched it. The destination would be reached by a species that may no longer recognize itself. This is not a matter of poor technology or lack of ambition. It is a structural problem built into how motion works in our universe. Every propulsion system we use today relies on the same basic idea: throw something backward to move forward. Chemical rockets burn fuel. Ion engines eject charged particles. Even futuristic nuclear concepts still depend on pushing mass in one direction to go the other way. Ostentalia's change, but the rule does not. And that rule comes with a price. The faster you want to go, the more energy you need. But energy has mass, and mass resists acceleration. As you add fuel to go faster, you also add weight, which then demands even more fuel. This feedback loop is known as the rocket equation. And it is unforgiving. Each small gain in speed becomes exponentially more expensive. By the time you start approaching relativistic speeds, the numbers explode beyond anything practical. This is where Einstein enters the story. More than a century ago, his theory of special relativity revealed that space and time are not independent. They are woven together into space-time, and that fabric enforces a strict rule. Nothing with mass can reach or exceed the speed of light. As an object accelerates, its energy increases, and so does its effective inertia near light speed. The energy required for even the smallest additional increase becomes infinite. This is not a technological limitation. It's not something better engines solve. It is the universe saying no. Particle accelerators confirm this daily. Subatomic particles are pushed to 99.999% of light speed, and as predicted, they behave exactly as Einstein described. Their mass increases, time slows for them, energy demands skyrocket. The closer they get to light speed, the harder the universe pushes back. So, for decades, faster-than-light travel was treated as a dead end. You could imagine it in fiction, but physics had spoken. The universe had a speed limit, and crossing it seemed as impossible as reversing cause and effect. Even reaching close to that limit creates problems at extreme speeds. Time itself begins to behave strangely for a fast-moving traveler. Clocks tick more slowly compared to those left behind. A journey that feels short to the crew could span decades or centuries back on Earth. You might leave knowing your family only to return to a world where everyone you knew has aged or vanished. Distance becomes separation not just in space but in time. Acceleration is another barrier to reach a significant fraction of light speed. Within a human lifetime, the forces involved would be lethal. The human body can withstand only limited acceleration before organs fail and bones break. You can stretch the journey over decades to reduce those forces. But then the distance problem returns. You trade survivability for slowness. This combination of limits creates a kind of cosmic trap. We can see other stars clearly. We can analyze their planets. We can measure atmospheres light years away and detect hints of water chemistry, even potential life. Telescopes have become astonishingly powerful, but physically reaching those worlds remains beyond our grasp. It's like standing on the shore of an ocean, able to see islands in the distance, but having no vessel capable of crossing the water. Before generations pass, and this matters for more than curiosity, our solar system is not a welcoming place. Every world beyond Earth is hostile in its own way. Too hot, too cold, too radioactive, too airless. Even the most promising candidates require technology. We don't yet have to support long-term human life. If humanity ever hopes to spread beyond Earth in a meaningful way, nearby star systems are the real prize. That is where planets exist that could resemble our own, yet those planets sit behind a wall of distance, reinforced by physics for a long time. Scientists assumed this was simply the cost of reality. The universe allows observation, but restricts travel. We could learn, but not go. We could map the cosmos, but remain confined to our small neighborhood. The stars would stay forever beyond reach, separated not by lack of desire, but by the structure of space-time itself. But science has a habit of advancing. When someone questions the framing rather than the conclusion, instead of asking how to go faster, some physicists began asking whether speed was even the right concept instead of fighting space-time. What if space-time itself could be shaped after all? Gravity already does this. Massive objects bend space and slow time. The universe stretches and expands on its own. Space is not rigid. It moves, curves, and evolves. If space-time is flexible, then perhaps motion does not have to mean pushing through it. That idea sounds subtle, almost semantic, but it opens a door, a small one at first, a door that leads away from engines and fuel and acceleration, and toward geometry, structure, and the deeper behavior of the universe itself. And once that door is open, the impossible begins to look negotiable. That is where the story turns to see why the idea of warp-like travel is so disruptive. We need to understand just how deeply the speed of light is woven into the structure of the universe. This limit is not an arbitrary number chosen by physicists, and it is not merely the speed at which light happens to travel. It is a fundamental property of space-time itself, a boundary that shapes how cause and effect unfold across reality. When Einstein introduced special relativity in the early 20th century, he overturned the old idea that space and time were fixed and absolute. Instead, he showed that they are flexible, interconnected, and dependent on motion. Time can slow down, lengths can shrink. Events that appear simultaneous to one observer may not be simultaneous to another, and at the center of all of this sits a single constant, the speed of light. What makes this constant so strange is that it is the same for everyone. No matter how fast you're moving, light always moves away from you at the same speed. This defies everyday logic, but experiments have confirmed it again and again. To preserve this rule, space-time itself must adjust. Time stretches, space contracts, reality bends to keep light speed unchanged. From this falls a consequence that feels almost cruel. As an object with mass accelerates, its energy increases. And that energy behaves like additional inertia. The faster you go, the harder it becomes to go faster still, near light speed. This resistance becomes overwhelming. The equations show that reaching the speed of light would require infinite energy, not a large amount, not an impractical amount, infinite. That single word closes the door on conventional faster-than-light travel. You cannot build an engine that produces infinite energy. You cannot store it. You cannot control it. The universe simply does not allow massive objects to cross that threshold by accelerating through space. This is why physicists often describe light speed not as a technological barrier, but as a structural one. It is embedded in how space-time works. What makes this even more restrictive is that the consequences appear long before you reach the limit. At high fractions of light speed, time dilation becomes dramatic. A traveler moving fast enough would experience time passing much more slowly than people back home. A round trip to a distant star might feel short to the crew, but decades or centuries could pass on Earth. Distance becomes a separation not just in space, but in history. This alone would reshape human exploration missions, would no longer be shared experiences. Travelers would return to civilizations that had moved on without them. Languages would change. Cultures would evolve. The universe would not just be far away, it would be out of sync. Acceleration adds another layer of difficulty. To reach even a modest fraction of light speed within a reasonable time frame requires enormous and sustained acceleration. Human bodies are not built for that. Even advanced life support systems cannot protect against the forces required to push a spacecraft to relativistic speeds quickly. Stretch the acceleration over decades, and the forces become survivable. But the journey becomes glacial speed, and biology pull in opposite directions for generations. Physicists accepted this as the final answer. The universe could be studied, mapped, and admired, but not crossed. Faster-than-light travel belonged firmly in the realm of fiction, alongside perpetual motion machines and time machines that violated causality. But there was a subtle detail hidden in Einstein's work that would later change the conversation. While relativity forbids objects from moving through space faster than light, it says nothing about how fast space itself can move. This distinction sounds trivial at first, almost like wordplay, but cosmology shows it is anything but. On the larger scales, space is not static, it expands. In fact, regions of the universe are receding from us, faster than light, not because galaxies are moving through space at those speeds, but because the space between us and them is stretching. This does not violate relativity, because nothing locally outruns light. Space-time itself is doing the moving. This realization cracked open a narrow conceptual gap. If space can expand faster than light naturally, then perhaps motion does not always require acceleration through space. Perhaps there are ways to exploit the geometry of space-time itself rather than fighting against it with engines and fuel. This idea required abandoning the intuitive picture of movement as something that happens within space, like a ship crossing an ocean. Instead, it suggested a deeper view where space itself is part of the mechanism, not a stage, but a participant. At first, this line of thinking seemed purely academic, interesting to contemplate, but disconnected from reality. Yet, physics has a history of ideas that begin this way only to later reshape technology entirely. General relativity itself was once seen as an elegant but impractical theory, until GPS satellites revealed that without accounting for time dilation, modern navigation would fail within minutes. The same equations that enforce the cosmic speed limit also describe how space-time bends, stretches, and flows. Gravity is not a force in the traditional sense. It is geometry. Massive objects reshape space. Time and everything else follows the curves. If geometry governs motion, then changing geometry could change what motion means. That is the pivot point. Instead of asking how to make a spacecraft go faster, some physicists began asking whether you could make space-time do the traveling for you, not by violating relativity, but by using it fully. The ship would not outrun light locally, it would remain at rest. Within its own region of space-time, while the space-time around it moved, this approach does not ignore Einstein's speed limit. It sidesteps it, but sidestepping a rule written into reality comes at a cost. Manipulating space-time is not like adjusting an engine throttle. The energies involved are immense, the mathematics is unforgiving, and the consequences, if misunderstood, could be catastrophic for years. These ideas remained on the fringes of theoretical physics. They were mathematically allowed, but physically absurd. The numbers didn't work. The energy demands dwarfed anything imaginable. The concepts lived in journals, not laboratories. Still, the fact that the equations allowed them mattered. Physics does not grant many loopholes. When one appears, even a narrow one, it demands attention. The speed of light remains absolute for objects moving through space. The truth has not changed, but the realization that space itself is dynamic, that it can stretch, compress, and flow, introduced. a new way of thinking about travel across cosmic distances. The barrier was no longer speed alone. It was control. Could space-time be shaped deliberately rather than passively endured? Could its geometry be engineered the way we engineer bridges, circuits, and reactors? Or was this flexibility only available to the universe itself, not to anything built within it? These questions mark the moment when faster-than-light travel shifted from fantasy to legitimate scientific inquiry, not because it had been solved, but because the rules no longer forbade it outright. And once that happens, impossibility becomes something far more dangerous. It becomes a problem waiting for a solution. That solution, if it exists at all, would not come from better engines or lighter fuel. It would come from learning how to sculpt space-time itself. That is where the idea of warp-like motion truly begins. Once physicists seriously entertained the idea that space itself could move, the problem of faster-than-light travel stopped being about speed and started being about shape. If motion through space was forbidden, perhaps motion of space was not that shift. May sound subtle, but it represents one of the most important conceptual pivots in modern theoretical physics. Space-time, according to general relativity, is not an empty container. It is a dynamic structure that responds to energy and mass. Planets curve it, stars dent it, black holes tear it so severely that not even light can escape. These effects are not metaphors, they are measurable, testable features of reality. GPS satellites must account for time flowing differently in orbit than on Earth. Gravitational waves ripple through space-time when massive objects collide. The universe constantly demonstrates that space-time can bend, stretch, and move. The question was never whether space-time could be manipulated. Nature does it all the time. The question was whether anything intelligent could learn to do it deliberately. In 1994, a physicist named Miguel Alcubierre asked a deceptively simple question. If general relativity allows space-time to curve in extreme ways, could it be arranged in a configuration that moves a region of space faster than light without violating any physical laws? He was not trying to build a spaceship. He was exploring the mathematics of Einstein's equations, looking for solutions that had been overlooked. What he found surprised everyone. Alcubierre discovered that the equations of general relativity permit a very strange geometry. In this configuration, space-time contracts in front of a region and expands behind it. The region itself, think of it as a bubble, remains locally flat and, calm inside, nothing accelerates. Time flows normally. Physics behaves exactly as it does on Earth, yet the bubble as a whole can move arbitrarily fast. Relative to distant observers, this was not science fiction logic. It was rigorous mathematics derived directly from Einstein's field equations. The key insight was this. Relativity forbids objects from moving through space faster than light, but it places no universal limit on how space-time itself can change. In fact, the universe already does this on cosmic scales. During the early moments after the Big Bang, space expanded far faster than light, carrying regions of the universe away from one another without violating relativity. Even today, distant galaxies recede faster than light. Due to cosmic expansion, Alcubierre's idea essentially shrank that cosmic behavior down to a controllable, localized scale. To visualize it, imagine standing on a moving walkway at an airport. You're not walking faster than your physical limits allow. You're standing still relative to the surface beneath your feet, yet you move quickly relative to the terminal because the walkway itself is moving. In Alcubierre's model, the spacecraft is standing still in its own space-time, while space-time itself does the traveling. Inside the bubble, there is no acceleration, no crushing forces, no time dilation relative to Earth. Crew members would not experience the brutal effects associated with near-light-speed travel. They would feel at rest while the universe reorganizes itself around them. This solved multiple problems at once. The speed limit no longer applied in the usual way because nothing locally exceeded light speed. The energy problem shifted from infinite to finite. The biological limits of acceleration disappeared, even time dilation. The cruel separation of travelers from their home era vanished. The ship would arrive without returning centuries younger or older than everyone else. On paper, it was astonishing. But there was a catch, a massive one. The space-time geometry Alcubierre described required an exotic form of energy, not antimatter, not dark matter. Something stranger, his equations demanded regions of negative energy density, energy that behaves opposite to everything we normally observe, instead of pulling space-time inward like mass does. This energy would push it outward. Negative energy is not something we encounter in daily life. Every known form of matter and energy we observe has positive energy density. Gravity attracts mass, curves space-time inward. The Alcubierre bubble, however, requires a ring of space-time that curves the wrong way. This raised immediate skepticism. Many physicists initially dismissed the idea, not because the math was wrong, but because the required ingredients seemed fictional. Alcubierre himself did not claim the drive was practical. He presented it as a mathematical possibility, not a blueprint. Still, the fact that the equations allowed such a structure changed the conversation permanently. For the first time, faster than light. Travel existed within accepted physics, not outside it. The energy estimates were brutal. Early calculations suggested you would need more energy than the mass of entire planets. Converted into exotic negative energy just to create a small bubble that put the concept far beyond any imaginable technology, yet even here, something important had shifted. The energy requirement, while enormous, was no longer infinite. That alone made it fundamentally different from conventional. Faster-than-light schemes, physics treats infinite requirements as absolute impossibilities. Finite requirements, no matter how large, are engineering problems. At least in principle, as researchers revisited Alcubierre's work, they noticed that the extreme energy demands were tightly linked to the shape and thickness of the warp bubble. The original solution was elegant mathematically, but not optimized. Small changes in geometry had dramatic effects on the numbers. This sparked decades of theoretical refinement. Physicists explored alternative bubble shapes, smoother space-time transitions, and oscillating configurations that could reduce energy demands by orders of magnitude. Each refinement shaved away another layer of impossibility. The required energy dropped from planetary scales to something closer to large asteroids, then further still far beyond our reach. But no longer cosmically absurd. More importantly, these refinements reinforced a deeper point. The challenge was not breaking physics. It was learning how to sculpt space-time efficiently at the same time. Experimental physics began offering faint but intriguing hints. Quantum theory predicts that even empty space contains fluctuating energy. Virtual particles constantly appear and disappear, creating measurable effects. Under the right conditions, in certain laboratory setups, scientists can create regions where the energy density of space differs slightly from its surroundings. These effects are tiny, but they are real. Some experiments have reported space-time distortions consistent with theoretical warp-like geometries at microscopic scales, not propulsion, not movement. But the correct shape of space-time emerging under controlled conditions for the first time, the warp concept was no longer confined entirely to chalkboards and simulations. This did not mean warp drives were close. Far from it, scaling such effects from nanometers to meters remains a staggering challenge, but it changed the status of the idea. Warp-like space-time manipulation was no longer purely speculative. It had crossed into the realm of experimental inquiry. Another unexpected avenue opened as well. If warp bubbles manipulate space-time, they should leave detectable signatures. Space-time distortions propagate as gravitational waves. We already detect these waves from black hole mergers and neutron star collisions. Theoretical models suggest that a moving warp bubble would produce a distinct gravitational wave pattern, one unlike any known natural source. This raised a provocative possibility. If any advanced civilization had already developed warp technology, even briefly, their movements might be detectable across vast distances. The universe itself could act as a record, carrying faint echoes of engineered space-time distortions. No such signals have been confirmed, but the fact that we can even ask the question highlights how far the discussion has moved. Faster-than-light travel is no longer dismissed outright. It is scrutinized, modeled, and searched for at its core. The Alcubierre idea reframes motion itself. It suggests that the universe's deepest limitation is not speed, but control. Space is flexible, space-time is malleable. Oh, cosmos is not a rigid grid, but a dynamic fabric. Nature bends it effortlessly. The challenge is whether intelligence can ever do the same. Warp travel, if it proves possible at all, will not come from brute force. It will come from precision, from understanding space-time so deeply that we can shape it gently rather than tear it violently. From learning how geometry, energy, and quantum effects interact at the most fundamental level. This is why the idea persists despite its difficulties. It offers something no other propulsion concept does. A way to cross cosmic distances without fighting the universe, without paying the usual cost of speed, time, and survival. It transforms interstellar travel from a generational ordeal into a navigational problem. Whether humanity ever achieves this remains unknown, but the mere fact that space-time itself can serve as an engine marks a turning point in how we think about the cosmos distance. Once seen as an unbreakable barrier becomes a feature of geometry, and geometry, unlike speed, can be shaped as warp physics evolved from a provocative idea. Into a serious scientific pursuit, one obstacle steadily rose above all the others and refused to fade into the background. It was not the mathematics and it was not the geometry of space-time itself. It was energy. Specifically, the kind of energy the universe does not readily provide. Everything we know about physics begins with a simple assumption. Energy is positive. Mass has weight. Gravity attracts objects, fall inward, not outward. Planets orbit stars because space-time slopes toward mass like a valley. This behavior is so consistent that it feels less like a rule and more like a personality trait of the universe. Reality prefers cohesion. It pulls things together. Warp geometries demand the opposite behavior. To contract space in front of a spacecraft, while expanding it behind, space-time must be pushed outward in carefully shaped regions. That outward curvature requires energy that behaves in a fundamentally unfamiliar way. Energy that reduces space-time's tension instead of increasing it. In technical language, it requires negative energy density. At first, this seemed like the end of the discussion. Negative energy sounded like a mathematical curiosity, something that appears in equations but never in nature. After all, we have never held a piece of negative energy in our hands, never stored it in a battery, never seen it accumulate in a container. Every everyday experience tells us that energy adds, not subtracts, but modern physics, especially quantum theory, has a way of undermining intuition. According to quantum mechanics, empty space is not empty. Even in a perfect vacuum, fields fluctuate constantly, virtual particles. Flicker into existence and vanish again, borrowing energy for unimaginably brief moments before returning it. This restless activity gives space a baseline energy level, often called vacuum energy. It cannot be seen directly, but it leaves measurable fingerprints. One of the most important demonstrations of this is the Casimir effect, when two uncharged metal plates are placed extremely close together. Quantum fluctuations between them are restricted. Certain wavelengths of virtual particles cannot fit in the narrow gap, while they remain free to exist outside the plates. This imbalance creates a pressure difference that pushes the plates together, producing a force with no classical explanation. What matters here is not the force itself, but what it reveals. The space between the plates contains less energy than the surrounding vacuum. Relative to its environment, it behaves as a region of negative energy density. This effect has been measured repeatedly, confirmed experimentally, and integrated into modern physics. Negative energy, in this limited and highly controlled sense, is real. That realization did not solve the warp energy problem, but it fundamentally changed its nature. The question was no longer whether negative energy could exist at all. The question became whether such effects could ever be amplified, shaped, and sustained on scales large enough to matter. The immediate answer was discouraging. Casimir effects operate over distances measured in nanometers, and their strength drops off rapidly as separation increases. Scaling them up from microscopic gaps to meter-scale structures would require extraordinary precision and stability, pushing materials and control systems far beyond current capabilities. Even optimistic estimates suggested energy demands that dwarfed anything humanity could generate. Still, the door was no longer locked. At the same time, theorists revisited the original warp models with a more practical mindset. Miguel Alcubierre's initial solution had been designed for mathematical clarity rather than efficiency. It assumed thick warp bubble walls and abrupt space-time transitions because those were easier to describe analytically. When researchers began relaxing those assumptions, smooth gradients reshaping the bubble, allowing dynamic rather than static configurations, the energy requirements began to fall, not slowly, but dramatically. Small changes in geometry produced enormous changes in the numbers. Energy demands dropped by orders of magnitude, transforming the problem from one that required planetary-scale resources into one that, while still far beyond reach, no longer violated common sense about the universe's limits. The required energy was still extreme, but it was finite and sensitive to design. That distinction mattered in physics. Infinite requirements signal impossibility, finite requirements signal ignorance and difficulty. This shift encouraged experimental work, and that is where the conversation changed. Tone entirely, instead of asking whether a spacecraft could be propelled, researchers began asking whether the space-time geometry itself could be created. Even briefly, and at microscopic scales, the goal was validation rather than motion. If the predicted distortions existed at all, then warp physics belonged to reality, not just a paper. In the early 2000s, experiments associated with NASA-affiliated researchers explored this idea using highly sensitive instruments and carefully arranged electromagnetic systems. The effects they searched for were extraordinarily small. Buried beneath noise and environmental interference, no propulsion was expected, only geometry. What they reported was subtle but significant. Measurements suggested space-time behaving in ways consistent with theoretical warp configurations, not as movement but as structure. The distortions were tiny, fleeting, and far from useful, yet they aligned with predictions rather than random fluctuations. That alignment mattered more than scale. Physics does not require practicality to acknowledge existence. If a phenomenon can occur at any scale, then it belongs to the universe's allowed behaviors. From there, the challenge becomes one of growth rather than permission. Even so, the energy problem remained dominant. Creating a warp-like distortion is one challenge, maintaining it stably is another. Warp fields require continuous control over extreme energy gradients, and any instability could cause asymmetric collapse, potentially releasing dangerous radiation or trapping systems in distorted space-time. Unlike engines which can fail locally, warp systems interact with the structure of space itself. This is where an even stranger idea entered the discussion, one that remains unresolved but difficult to ignore. Dark energy is the mysterious component driving the accelerating expansion of the universe. It accounts for roughly 70% of all energy that exists, yet it does not clump, radiate, or behave like any known form of matter. Its defining feature is negative pressure, a tendency to push space apart rather than pull it together. That property is uncomfortably similar to what warp geometries require. Some physicists began to wonder whether dark energy and the negative energy densities needed for warp fields were related, perhaps even manifestations of the same underlying phenomenon. If space-time already contains an energy component that naturally drives expansion, then warp technology might depend on learning how to modulate or redirect that behavior locally. Rather than manufacturing something entirely new, this idea remains speculative. We do not know what dark energy is, how it behaves at small scales, or whether it can be influenced at all. Yet the possibility that the universe already contains the required ingredient everywhere reframes the problem profoundly. Instead of creating exotic energy warp drives, might rely on understanding and shaping a property of space-time that already exists. Even without invoking dark energy, the energy challenge has transformed how physicists think about propulsion. Warp drives are not engines in the traditional sense. They do not burn fuel or exchange momentum. They are space-time control systems, requiring constant feedback, stability, and precision at levels that stretch current engineering imagination. Progress in this field does not look dramatic. It does not involve launches or explosions. It looks like improved sensors, refined simulations, and quiet laboratories measuring effects most people would dismiss as background noise. Yet history suggests this is exactly how foundational. Technologies begin flight required understanding air before wings. Nuclear power required understanding atomic structure before reactors. Warp travel requires understanding vacuum energy and space-time geometry before motion. The energy wall remains immense, and it may resist us for generations, but it no longer stands as an absolute prohibition. Instead, it has become a test of understanding, asking not whether we can overpower the universe, but whether we can learn to work with it at its deepest level. If space-time can be shaped deliberately, and energy can be guided rather than consumed, then any attempt to do so would inevitably disturb the fabric of reality itself. Those disturbances would not remain confined to laboratories or theoretical models, because space-time carries information, propagates change, and leaves signatures that can travel across vast distances. The moment a civilization learns to sculpt space-time, it stops moving silently through the cosmos and begins to announce its presence in ways the universe itself can record. Once physicists accepted that warp-like space-time distortions might be physically possible, an unexpected question emerged, one that shifted attention away from building such technology and toward something far more subtle. If space-time can be deliberately shaped, then those distortions should leave traces behind. And if traces exist, then perhaps the universe itself could reveal whether faster than light. Travel has already occurred somewhere else. This idea rests on a fundamental fact. Space-time is not silent. When massive objects accelerate or when space-time changes shape, it responds by sending out ripples. Known as gravitational waves, these waves are distortions of space-time itself, stretching and compressing space as they pass, carrying information about the events that created them. For most of human history, gravitational waves were purely theoretical. Einstein predicted them in 1916, but even he doubted they would ever be detected. They are extraordinarily weak by the time they reach Earth, diluted across unimaginable distances. Yet in 2015, detectors finally observed them. Two black holes collided more than 1 billion light-years away, and the faint tremor they produced was measured here, smaller than the width of a proton. That moment changed physics permanently. It proved that space-time carries messages across the universe, and that with sensitive enough instruments, we can read them. Since then, dozens of gravitational wave events have been detected, each one a violent cosmic event recorded directly in the fabric of reality. This success led to a provocative idea. If black hole collisions generate gravitational waves, then engineered space-time distortion should do the same. A warp bubble is not a gentle adjustment. It involves sustained compression and expansion of space-time as it moves. According to general relativity, such behavior must produce gravitational radiation. Crucially, the pattern of that radiation would differ from natural astrophysical sources. Black hole mergers produce brief rising chirps. Neutron-star collisions leave different signatures. Shaped by nuclear matter, a warp bubble, by contrast, would generate a persistent directional space-time disturbance, moving coherently rather than erupting briefly. Simulations suggest such a signal would be difficult to confuse with known cosmic events, provided detectors are sensitive enough. This opened a remarkable possibility. Instead of waiting centuries to develop warp technology ourselves, we could search for evidence that someone else already has. In recent years, researchers have modeled what a moving warp bubble would look like to gravitational wave. Observatories, these studies predict distinct frequency ranges and polarization patterns tied to the geometry and motion of the space-time distortion, while no confirmed detections exist. Yet gravitational wave astronomy is still extremely young. We have been listening seriously for less than a decade using instruments only just capable of detecting the loudest events in the universe. That is about to change over the next decade. Upgrades to existing detectors and the deployment of space-based observatories like LISA will dramatically expand our sensitivity, especially at lower frequencies, where some warp-like signatures are expected to appear. If an advanced civilization anywhere in our cosmic neighborhood uses space-time manipulating technology, even sparingly, it could leave behind ripples that propagate outward for millions or billions of years. Those ripples would arrive long after the craft itself has passed, carrying information about its structure and motion. In effect, spacetime would preserve a fossil record of advanced technology. This turns the search into a form of cosmic archaeology. We would not need to see spacecraft directly or intercept communications. We would only need to identify a space-time signal that cannot be explained by known astrophysical processes. The universe would supply the data. Our role would be interpretation. The implications are extraordinary. A confirmed detection of an engineered space-time signature would immediately answer two profound questions. It would confirm that we are not the only technological civilization in the universe. And it would demonstrate that faster than light travel is physically achievable. The debate would shift overnight from possibility to replication. Even more significantly, such a detection would offer guidance. Gravitational wave signals encode information about the systems that produce them. By analyzing a warp-like signature, physicists could infer bubble geometry, energy distribution, and propulsion dynamics. It would be a form of reverse engineering at cosmic distances, extracting design principles from space-time itself. This approach is not unprecedented. Humanity has often learned how nature works by observing. Before building, we understood stellar fusion. Long before we constructed reactors, we mapped planetary motion. Centuries before launching spacecraft, observation has always guided engineering. Still, caution is essential. Many cosmic phenomena remain poorly understood, and misinterpreting a signal would be a serious mistake. Any claim of engineered spacetime would require overwhelming evidence, independent verification, and years of scrutiny. There are also unsettling possibilities. Advanced civilizations might deliberately minimize detectable spacetime signatures, much as modern technologies reduce emissions to avoid detection. Warp travel might be rare, tightly controlled, or restricted to regions far from observers, or it may carry risks we do not yet understand, discouraging widespread use. Silence itself would still be informative. If increasingly sensitive detectors find nothing, it may suggest that warp travel is extraordinarily difficult, extremely rare, or constrained by deeper physical principles that knowledge would still guide research, narrowing the path forward. What makes this search so powerful is that it relies on established physics. Gravitational waves are real. Space-time distortions are real. The connection between warp geometries and gravitational radiation follows directly from general relativity. No new laws are required, only new questions in this sense. The universe becomes our laboratory. Every major event leaves an imprint in space-time, and those imprints travel outward indefinitely. Somewhere within that vast archive may lie evidence of technologies far beyond our own. We only need to learn how to listen carefully enough. And if one day we do find such a signal, it will not arrive with fanfare. It will appear quietly, buried in data, until its meaning becomes impossible to ignore. At that point, faster-than-light travel would no longer be a distant ambition. It would be something the universe has already proven can be done. If warp-like travel ever becomes real, its impact would extend far beyond propulsion systems and spacecraft design. It would represent a fundamental shift in how humanity relates to the universe, because faster-than-light travel is not merely about reaching distant places more quickly. It is about dissolving one of the oldest constraints that has shaped civilization, the tyranny of distance. For all of human history, distance has dictated what was possible. It determined how far ideas could spread, how cultures evolved, and how civilizations rose and fell. Even our greatest technological leaps, ships, trains, airplanes, rockets, never truly escaped this rule. They reduced travel time, but they never removed the barrier itself. Distance still mattered. Time still accumulated. Separation still carried a cost. Warp travel would change that relationship entirely. Stars that now exist only as abstract points of light would become reachable destinations, not symbolic goals for distant generations, but places that could be visited, studied, and returned from within a single lifetime. The night sky would stop being a static backdrop and start becoming a navigable landscape, one where routes and distances are measured not in millennia, but in years or even weeks. This shift would immediately transform scientific exploration today. Astronomy is largely an exercise in inference. We analyze light spectra and gravitational effects to understand objects we can never touch. Even our most detailed observations remain indirect. Warp travel would replace inference with presence. Instead of modeling exoplanet atmospheres, we could sample them. Instead of guessing about alien geology, we could walk across it. Entire branches of science would move from remote sensing to direct experimentation. The pace of discovery would accelerate dramatically. Feedback loops that currently take decades or centuries would compress into human timeframes. A mission could leave, gather data, encounter unexpected phenomena, and return with answers fast enough to reshape theories while the same generation of scientists is still alive. Knowledge would no longer crawl across cosmic distances. It would move with intention. Colonization, too, would enter a new category of possibility. Today, even Mars represents a monumental challenge, one that stretches resources, psychology, and logistics to their limits. Worlds orbiting other stars are beyond serious planning, existing only in speculative discussions and distant dreams. Warp travel would not make colonization simple, but it would make it conceivable. Entire star systems could be surveyed systematically. Worlds could be evaluated for habitability, stability, and long-term potential. Human expansion would no longer hinge on reshaping hostile environments close to home, but on choosing environments that already support life. That difference matters profoundly. A species confined to one planet is fragile. A species spread across multiple star systems is resilient in a way that reshapes its future entirely. Natural disasters, asteroid impacts, climate catastrophes, even stellar evolution itself would no longer represent existential threats. Survival would become distributed, rather than centralized, yet this expansion would carry risks as significant as its rewards. Technologia warp would be the most powerful tool humanity has ever developed. And power amplifies intention rather than replacing it. A system capable of manipulating spacetime could be used for exploration, cooperation, and survival. But it could also be weaponized in ways that current frameworks struggle to imagine. Control over distance is control over access, and control over access, inevitably, intersects with power. History offers little comfort here. Every transformative technology from metallurgy to nuclear energy has been used both constructively and destructively. Warp travel would magnify that duality. Without global cooperation, shared governance, and ethical restraint, the same tool that opens the stars could deepen division and conflict. There are also physical unknowns that cannot be ignored. We do not yet understand whether repeated spacetime manipulation could produce cumulative effects. Spacetime is resilient, but it may not be infinitely forgiving. Just as ecosystems tolerate small disturbances but collapse under sustained stress, the fabric of the universe may have thresholds we have not yet identified. Warp travel might demand limits not because of politics or morality, but because of physics itself. And then there is the psychological dimension, one that technology alone cannot solve. Humans evolved within narrow spatial boundaries. Our sense of home, identity, and belonging is deeply tied to place. Becoming an interstellar species would stretch those concepts in unpredictable ways. What does it mean to belong to a planet when reaching another star? Is no longer extraordinary? How does culture evolve when separation loses its power to isolate? History suggests that expansion reshapes identity as much as geography. Isolation breeds divergence. Connectivity breeds convergence. Warp travel could do both simultaneously, creating a civilization unified by access, yet diversified by environment. Entire branches of humanity might adapt to different worlds, different skies, different rhythms of day and night. The concept of human itself could begin to blur. But perhaps the most unsettling implication lies beyond humanity's internal changes. If warp travel is possible, and if space-time manipulation leaves detectable signatures, then success would not necessarily make us pioneers. It might reveal that we are late to the conversation. The universe may already contain civilizations that solved these problems long ago, quietly shaping space-time in ways we're only beginning to detect. In that context, developing warp travel would not just be a technological achievement, it would be an announcement, an admission that humanity has learned to write its presence into the fabric of the cosmos itself in a language space-time understands. That realization reframes the entire endeavor. Warp travel is not simply about reaching outward. It is about becoming visible on a cosmic scale, about crossing a threshold where our actions no longer remain confined to a single star system, but echo across vast regions of the universe. Whether that visibility is welcomed or ignored is beyond our control. What remains within our control is how we approach the challenge, warp travel. If it comes, will not arrive as a sudden miracle. It will emerge from decades of quiet work, incremental advances, and careful restraint. It will require not just intelligence, but patience, not just ambition, but humility. Because shaping space-time is not like building a faster engine, it is an interaction with the universe. At its deepest level, every mistake carries consequences that propagate outward, not just through space, but through time. And that brings us to a sobering truth. The question of faster-than-light travel is no longer purely scientific. It is philosophical. It forces us to ask what kind of species we intend to be, once distance no longer protects us from ourselves. Once the stars are no longer distant abstractions but reachable realities, will we expand with care, curiosity, and respect for the environments we encounter? Or will we carry old conflicts into a much larger arena, magnifying their consequences beyond anything history has prepared us for? The universe will not answer these questions for us. It will only respond to what we choose to do if warp travel becomes possible. It will mark the moment humanity transitions from a civilization defined by limitation to one defined by responsibility. The stars will not judge us, but they will remember us. Because space-time does not forget disturbances written into its structure. In the end, the true significance of faster-than-light travel may not be how far it allows us to go, but how clearly it forces us to see ourselves. For now, faster-than-light travel remains unfinished business. The equations exist, the loopholes are real, the experiments are quiet, subtle, and incomplete. We're no longer in a universe that says never, but we are not yet in one that says now. And that space in between is where the most important moments in science usually live. Every major leap in human capability began this way, with ideas that felt unreasonable until evidence slowly removed excuses to ignore them. Flight sounded impossible until air itself became understood. Nuclear energy was dismissed as fantasy until atoms revealed their structure. Each time the universe did not change its rules, we changed our understanding of them. Warp-like travel sits at that same threshold. It may turn out that the energy demands never yield, that deeper laws step in to protect causality, or that space-time resists sustained manipulation in ways our equations cannot yet predict. If that happens, the effort will still have mattered, because it will have taught us something fundamental about the limits of reality and our place within it. But if the universe allows this path even narrowly, then the future opens in ways that reshape human history, not instant access to everything. Not unlimited freedom, but something far more meaningful, the ability to explore our cosmic neighborhood on human timescales, to turn distant stars from unreachable symbols into reachable horizons. The question is no longer whether the universe is vast enough to explore. We already know it is. The real question is whether we will learn enough, patiently and responsibly, to step beyond the boundaries that want to find us somewhere written into space-time itself. The answer may already exist. If you liked the video, don't forget to leave a like and subscribe. It makes a huge difference and helps the channel grow.